And we can remove the parentheses here. All right. So that's the logic. That's the logic for the summation. Again, 1 bit or 3 bit adder. 1 bit full adder. Now let's look at the carry out. Look at this column. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. How to group them? How to group them? In order to get rid of static hazard, remember that still? That's a better way to do it, but not the only way to do it.
Can you group the bottom one?
No, 3 of them, no, they're not simplifying. You can, but it's not working, not helping. So either 2 or 4 or 8. Why? Why 3 is not working?
Because 1 bit changes.
1 bit changes. If you have another one, the third one, then both of the digits are flipping. So you have to use that one either being grouped with one of the first 2 ones each time. You know what I mean? Okay. So let's look at this one first. So CL equals BCI. So this bit is being flipped. That's why you can cancel it. So I'm looking at these two, BCI, or these two are getting you A first, and then see which one is being flipped. So just cancel it. B is being flipped. So I only have CI left. And these two have A, and B is not flipped, but CI is flipped. It's just this, right? This is the simplified version of the C carry out. And this equals okay. So this is the logic equation for this for carry out. How do we design the circuit out of it? Schematic. A, B, C, I. We need the XOR gate. Connect A and B. Output. We need another 2-input XOR gate. So which one? Wait, what I'm doing here? Sorry. So what's the final output here? So A XOR B XOR CI, right? It's only this only option for S. So you cannot group anything, and that's the flatter's logic. Follow this one. You can group in different ways. Group these two and leave this one, single all this one, or just group these two, whatever. There are probably C A XOR B sometimes in some other forms, but I can tell you it's not a ideal way to do it. So this is a lot better than that. Static hazard if you leave one out, right? That's why I don't want to do it. That's why I want to group all of them together. So this is a lot better choice. But still, you know, from the textbooks, a lot of people are still using A XOR B. Why? It's making no sense.
Does it reduce the number of gates using XOR?
Not really. It's just changing the OR logic to XOR logic. The XOR gate is even more number of gates. It's not making sense. Yeah. So these people have never built it, right? Well, people who are teaching logic, but they're just teaching the symbols. If you go to 90% of the schools in the US, they are going to learn that kind of shit. They just never let you build a game. I'm telling the truth. They are teaching logic, but they don't know how to build the gates. So what's the circuit for this CL? Definitely not the best way to do it, right? That's why we want to learn AI logic. I think in the lab you did this, right? Did you? The what the yeah, for the slider, yeah. Oh, you didn't look at it?
No, we didn't look at the schematic. We did it from the.
Oh, really? Oh, did we use?
Yeah, we looked at the schematic, but we didn't look at the layout.
Yeah.
This is more fun though, actually.
It's such a pain. I got like 8 colored pencils. I was going there, but then I'd like do the line in the wrong pencil and like scribble it out with the other one, and then it like I couldn't tell what it was doing anyway. So then it just made it worse and made it take longer.
Yeah. Probably better to draw it on the iPad or.
Yeah, I thought it would be really smart with all my colors and stuff, and then it just made it worse. I like was using it to like cross out which lines I had drawn on my thing, and then I ended up with just like a bunch of X's all over it, and I didn't actually know what I had done.
Yeah, makes sense. Since you're in Colorado, we want to make it colorful. Right?
And you recommended us to do multiple colors for different wires.
Yeah.
So I tried to get back there.
Should I say thank you? Or
What?
should I just say thank you? Good job. Yes, good job. So let's see a 3-bit, since this is something we're going to build in the homework assignments or in the lab. So for a 3-bit slider, so the slider I just showed you guys here is called a ripple carry slider. Let me write down the name. Why? Because the carry out of each FA is the carry in of succeeding.
Wait, so I have ones where you don't carry out is not the next carry in.
Carry out each is carry in.
Right, but the fact that you have to specify that does that implies that there's one that doesn't do that.
What do you mean doesn't do that? What do you mean?
Like, is there a version of those 2 or 3-bit full object adder that doesn't
We're not getting
carry
to
that
that.
to somewhere else?
There may be, but that's not what
Well, I'm just curious.
We'll see. We'll see if this will answer your question. So each carry bit get rippled into the next stage. So if I have a 3-bit, now it's a 3-bit slider. Again, I name it as C-1, so this is C0, C1. So this can be C2, right? What are these bits?
Yes.
Yeah, right.
Yeah, you know. No,
Wait,
maybe not A1.
So you're adding what? You're adding B2, B1, B0 to A2, A1, A0, right?
So
These are all the bits for the output. Ripple carry full adder. So how do you add a negative number of it? Add a negative number to a positive number. Subtraction, right? Subtraction. So this involves two's complement. Remember how to convert a number to its negative counterpart?
You take the number minus all ones, isn't it?
Yeah, in a two's complement system, right? If we are talking about the signed numbers, binary numbers, if I have 100, what is this number? Represents -0? So the best way to look at it is, what is this number here? So the MSB in the two's complement binary numbers is the negative that number. You know what I mean? This is 4, right? But this is actually -4. That's how I calculate it easily. Remember? That's a better way to do it. A lot of places will teach you that you have to convert it, flip every single bit and add a 1 to it. That's how you convert it. So for example, this is +3, right? How to find -3? You flip every single bit and add a 1 to it, and you are getting -3. It's okay. This takes more computational efforts in your brain for neurons to run. Yeah. You're doing great, actually. To its negative number. Let's do a couple more examples. For 0, 1, 0, 1. What is this number? In two's complement, okay? Yeah, 5. What is -5? What are the two ways to do it, right? What are the two ways to do it? First, flip it. Flip every single bit and add a 1 to it. So you're getting 1, 0, 1, 0 plus 1, right? What's the other way to do it? -5 is simply just a -a plus, yeah. It's a lot better than this, okay? So think about all the calculations that way in the future. All right. But when we are designing the circuit, this is difficult to implement. It's just something happening in your brain, but how do we implement it in using transistors? Your brain tells you this is -a. The computer is a binary machine. You have to do something like make it a -a in there. It's going to be binary again. But however, when we were doing the operation here, all the operations being used here can be implemented using digital logic. Why? Because flipping every single bit is doing what? Inverters, right? And add a 1 to the LSB is doing what? Adder. Done. So how can we convert a number into a negative number in order to do a subtraction, right? So it's going to be B2, B1, B0. I'm trying to do this, for example. This is what I want to do in the computer. So literally, you have to do this. Because there's no subtractor. We have a subtractor? No, we just learn a full adder. How to subtract it from it. Yeah, negate it and then add it here. Convert these ones to its negative form. How to convert to negative form? Flip it, add 1 to it. Let's see. Wait, another thought here. The reason we want to use a full adder to implement that subtraction is because we already have this infrastructure built in the circuit. We can use it as a full adder or a subtractor. However, if you just want to design the subtractor itself, but not a full adder, could you start from the beginning from the truth table? Yes, right? You just list all the combinations of the inputs and all these subtractions, the results here, and then maybe a carry, I don't know. The thing is, this is where you are doing tooth complement in the computer. Why not directly using the full adders to do it? So I'm going to show you how to flip these bits and add 1 to it on Friday. So design the full adder during the lecture and also start working on a fast, high-speed full adder. And you're going to lay it out maybe next Tuesday. And there's a homework assignment for Friday, but you are not ready for that anyway. So it's going to be a different structure of the full adder. It's called carry look ahead adder. Instead of learning everything just directly on the slides, this is what we went through in college. We're actually building it. So you are building a carry look ahead full adder. So this is a 3-bit ripple carry RCA ripple carry adder, and this is a carry look ahead adder. It's a different algorithm running behind the scene. And here's the schematic, and eventually you can see that. So C2 is a sign to show that if the adder is fast or enough, fast or slow. Why? Because the ripple carry full adder, C2 becomes the last bit to flip. Because it ripples to the front, and eventually you have to get the C2 ready in order to get the correct output. Right? That's why C2 is a sign here. And you can see that the first one is a RCA, and the second one is the faster one. See? Which one is faster? Just look at the C2. Whenever this is being flipped, it just compared to C1. But look at this one, this bit, or this spot here, and compare to the rising edge. Tell me which one's faster. Why? No. You want a C2 to happen earlier, right?
Yeah, absolutely.
Oh, yeah, the right, yeah, the right one is faster. Yeah, the right one's faster, right? It happens earlier. Only saves a few nanoseconds. All right. See you on Friday.